Hi all, this will be my first video from section 10.1, and the first thing I want to make clear is that we all know what a hypothesis test is. Now the example I gave in class, suppose a friend says he has a coin that's a fair coin and you want to test that claim. So this is your friend's claim. The claim is this is a fair coin. And so we're going to test that claim, of course, by flipping it. So the data that we collected is the proportion out of all the flips, how many are heads. And it turns out it's 100%. And that doesn't jibe with the idea that this is a fair coin. Our intuition already says, I don't think this is a fair coin. Now we might give him the benefit of the doubt and say, okay, maybe just by chance you got 12 heads in a row, but still, I'm not buying it. Next time we pick a movie, we're going to use my quarter, not your quarter. Okay, let's apply this to hypothesis testing now. Here's our claim, and I'm going to take that claim and I'm going to write in math. So, see if I can get this pen to work here. Here's the claim. The claim is that the proportion out of all the heads are that it's going to be 50%. So that would be the proportion is equal to 0.5. Now the complement of the claim is that P is not equal to 0.5. Don't need that just yet. What we need is the null hypothesis. The null hypothesis is going to be P is equal to 0.5. On the assumption that it's a truly fair coin, this should be true. We are going to assume this is true. I've forgotten how to use this pen. Now, if it's not true, then we're going to claim the alternative hypothesis, and that is going to be either the claim or the complement. In this case, it's the complement. It's going to be whichever one does not contain equality. Now, here's our data. We ended up with a p-hat of 100%. And that's not very probable if it is truly a fair coin. So what we're wondering is, what's the probability of getting p-hat of 100% given that the true proportion is 50%, 0.5. And that's going to be our p-value. That is the probability of seeing the data that we've collected under the assumption that the null is true. And it turns out our p-value is, well, we're going to get 12 heads in a row. P of heads and 12 of them, heads, if it is in fact a fair coin, so that the true probability of each heads is 50%, is going to be 1/2 times 1/2 times 1/2, 12 of these. In other words, it'll be 1/2 to the power of 12. I'm going to pause the video because I've forgotten what that's equal to. I'm just going to put this in my calculator. Okay, I've got an answer for you, and the answer is really tiny. So this is going to be, it's 0.12324. Really improbable. Pretty much by anybody's definition of improbable. Now we have a standard of what's considered improbable. That's our significance level. And we're going to compare this to that standard. But really, if it really is a fair coin, I shouldn't have gotten 12 heads in a row, or at least it's really improbable that I'm going to get 12 heads in a row. Okay, let me clear the screen here and I'm going to come up with a conclusion. So here's our conclusion. What we have concluded is if the coin is fair, it's improbable to get the results we got, the data that we collected. But we don't doubt the data. We don't doubt the data we got. Because we actually saw it. We saw with our own eyes 12 heads in a row. Instead, we reject the assumption. And that's what I'm talking about when I say we reject the null. Because the null is the assumption that we're assuming is true. So we reject that the coin was fair. So see, we do hypothesis tests all the time. Okay, so let's get into the rest of 10.1 and cover a few more details.